for joining us. Today we're going to be talking about LASIMM, which was the large-scale additive and subtractive integrated modular machine. It was an EU H2020 funded project that we worked on together from 2016 to the end of last year. Today it's me and Josh from Foster & Partners, and joined by Frank and Johnny from Autodesk. I work in the specialist modeling group at Foster & Partners. We're an internal research and development group. My interests and focus are around emerging new technologies that could be useful and that we're applying in the construction sector. Josh?
Hi, I'm Josh Mason from the specialist modeling group. I'm associate partner. I focus on complex geometry and integrated systems in construction and manufacturing. So I was responsible for integrating the beam design with all the constraints on the project.
Hi everyone, I'm Johnny van der Zwaar. I am a project lead at Autodesk, part of the collaborative research and innovation team. And in the LASIMM project, I was the work package lead for the software development.
Hi, I'm Frank Messmer, working in the same team as Johnny at Autodesk. I'm senior research engineer. I've been responsible for writing the software to drive the machine as well as its integration with the system. And also I've been participating in the manufacturing of the components.
Great, so I'm going to get us started and then we'll pass through to Josh, who will talk about the beam design, and then Johnny and Frank will talk about how we integrated the actual machine and the results that we got. So we're going to be talking about the large-scale 3D metal printing projects that Foster & Partners worked on with Autodesk and a number of other companies from across the European Union under an H2020 grant. So I'm going to give a bit of background about Foster & Partners' interest in 3D printing and our how we were trying to find value within this new technology within the construction industry. So our interest in 3D printing and rapid prototyping goes back over a decade now, with us investing in a number of rapid prototyping machines in our office, from SLS to SLA and 3D printers. We typically use these for models and producing parts for buildings to see them in sort of physically, to see them in 3D. One of the limitations of this that we found is that we're kind of limited by the material. So it's typically plastic, and also by the scale. So the parts we're making are limited to the machine size, rather than being able to produce these large scale components that we either at the sort of a large scale for models or directly for components for buildings. So this was an example of using plastic robotic spatial printing to produce a part that you can see on the mesh on the left, that we're adding density to the part where we think that simulations are telling us with areas of higher stress. And these parts can be sequenced in a single toolpath by applying this unitary typology to the toolpath, which is a lot of algorithms that we were developing for this to be able to enable this continuous printing sequence. We've also been sponsoring a PhD. This is from Arthur Pryor at the Bartlett, looking into hybrid clay printing for the automotive model making application. So being able to additively print wax and then machine away again as a subtractive process, and then interface this with a more manual modeling or sculpting process. Also worked with Branch Technology in Tennessee on the NASA Centennial Challenge for the Mars habitat, looking into, again, large-scale plastic printing, but this time bringing in basalt fibers into the polymer to potentially use in situ resource utilization on Mars. And another collaboration with ITKE in Stuttgart, looking into fiber winding of FRP, using these rigs rather than molds. And a project that I've been working on since my time at Foster's over the last 6 years, into large-scale concrete printing and the type of parts that we could make with that process. Rather than producing solid parts, we're interested in what type of added performance can we add to the concrete by bringing in sort of cavities for potentially for ventilation within a wall, or thermal insulation, or even acoustic attenuation, just through this control of the toolpath. Which brings us to LASIMM, which is part of this journey that we've been on, looking into additive manufacture. So the consortium is relatively large. It was 10 partners from across Europe. With 3 end users. There was us, Foster's representing the construction industry, Vestas, a wind turbine company in Denmark, and BAE Systems in aerospace. LASIMM were the experts on the subtractive process. Autodesk were in charge of the processing the parts so that they would be ready to print, and actually the software to control the machine. EWF, the European Welding Federation, were the project coordinators and in charge of training and developing standards. Global Robots in the UK were the robot system integration. Cranfield was where the technology was originally developed with the WAM, the wire and arc additive manufacturing. And also HZG and Technico Lisboa were in charge of extended system capability and material testing. So with this consortium, the real high-level aim was to build this machine and test it through a series of demonstrator parts, which would showcase technology and the value that it would potentially be adding. So you can see here we have the additive process on the bottom, the 2 WAM robots, the larger PKM parallel kinematic machine doing the milling, and then the parts on a plate on a part rotator in the middle. So the high-level objectives of the project, again, were reduction in time and cost of parts with respect to current processes like powder bed or blown powder, an increase in productivity for high-volume AM production, so being able to produce bigger parts faster than you would be able to do otherwise. Flexibility and robustness of the machine, so looking into the modularity of the different components, say you will be able to add more robots to be able to produce larger parts, or different processes as you like. And the software was a key part in being able to create that framework. Reduction of inventory, so being able to produce parts on demand, and a reduction of workfloor space by integrating a number of different processes into a single machine, and also contribution to standards and certification for hybrid processes. So WAM in a nutshell is basically a welding process attached to a robotic arm. So by controlling the movements of the arm and the welding parameters, we're able to deposit layers of weld onto a base plate and build up a part incrementally. We've done in a number of different materials, so steel or aluminium or even titanium, which you see here. And with these beautiful colors from the titanium. We've yet to find an application in construction for titanium parts, but we are looking. And with the hybrid process, you can start to see here. So it's printing a near net part, which is then milled back to a net shape part. This is comparable to, or in contrast to, say, casting, where you're producing a part and then there's a finishing process, or milling from a solid billet. So this allows us to actually print to roughly the right shape and then mill back to the exact shape that we want. So there's a number of constraints that come with this process that we sought to include in the design process that Josh is going to speak about in a bit when we were designing the demonstrator part. So, for example, we know that we're going to have a base plate that we're going to be printing on either side of. We know that the deposition speed is around 3 to 4 kilograms an hour. At the moment, although those can be larger, in the deposition, the bead diameter, roughly the size of the machine, and also minimizing the amount of material and the cost. These are some of the key constraints that we were involved in when we were designing the demonstrator. I think for us as well, we were really trying to look into where the added value was for this new process. So looking at it from maybe a spectrum from pure function through to pure aesthetics. So we've got maybe parts that are just purely structural and we don't care what it looks like, through to maybe sculptures, which we only care how it looks like. Obviously, this is quite a simplified scale, and it's quite nice to think about objects that you can start to combine these things. So things that do have a very strict function, but can also start to bring in the unique aesthetics that we get with the WAM process. So this breaks that down a bit more, so we can think about the value being added to the part itself through added functionality. So, for example, optimization, being able to produce parts that aren't solid, new ways to interface with other materials in that you might find in a building, and also ease of assembly. So being able to produce parts that, say, lock together, and also the aesthetics then of the parts. So we've got a lot of different things that we can play with here. A lot of this comes down to the process parameters that are built into the software. So how is the part sequenced, and what is the toolpath, and what are the aesthetics you get from this, and then how does that play in with the subtractive process, which results in this smooth surface finish. And there's also value in the process itself. So being able to, as with any 3D printing, be able to produce parts that do have added complexity that you wouldn't otherwise be able to make, being able to produce one-off bespoke components, which can help us with optimizing for local conditions within a building. So just to highlight again what the parts, what the value is that we wanted to highlight within the demonstrated components. So for it to be lighter and stronger than a traditional part, for it to be able to demonstrate the structural behavior of what was going on inside the part, showing the geometric freedom we can get from 3D printing and the part complexity, and also the aesthetics of the process and part consolidation, so bringing together more than one function within the part. This brings us back to some of the other earlier research that we've been doing in partnership with a PhD student, Alessandro, at the Royal Veterinary College, looking into how bones actually adapt to the different stresses that are going on within them. Bones are a fascinating example to look at for optimization. And we start to see these analogies coming through in topology optimization software at the moment. So for example, if you take a slice through bone, you can start to see that we're adding density into regions where we know that there's greater stress, and also the alignment of this microstructure against the loads. So looking at this on sort of much on a smaller scale, the researcher was able to look into the mechanisms that happen to drive this small scale structure. And this is actually changing over time as well. It's not a static. Your bones will change, and say if you go into space in a low gravity environment, your bones will lose some mass to deal with the lesser loads on them. So part of the research here was being able to translate this research into structures that we could potentially use in construction. So space frame structures is one example. So actually putting in a denser volumetric mesh into regions where we have higher tension or compression within parts. So some nice 3D prints that we made to showcase this transition from the FEA stress analysis to a wireframe mesh, and showing what can be done with this. So it's also allows you to go from regular volumetric meshes through to irregular unstructured meshes. And the savings that can be found within the components can be, I think we found up to around 30 or 40% material saving or added strength if you want to keep one fixed. And this journey that we had looking into where material can be placed within structural components to want to kind of optimize the parts for their local conditions, but also show off really what's going on inside the building. And this legibility of the structure is something that we're quite keen to progress further. Maggis Centre in Manchester was a nice example of this. It's a small building in the UK, these timber cantilever trusses forming these sort of wings jutting out from the building, which formed canopies in these interior exterior spaces. A lot of the development that went into these beams was looking into what would be the lightest, where we could remove material within the beams to maximize the structural performance of them. And also to make the structure as light as possible, to bring in daylight and make it feel like you're transitioning from an internal and external environment quite fluidly. So there's a lot of development going on with the beams and how we could, rather than using strict or black box generative software, we were interested in how we could design with the outputs from the FEA simulations. So looking into different patternings and different ways to influence the design of these glulam beams using the structural simulations. So the mock-up of one of the parts, we worked quite closely with the fabricator for. You can see we have a sort of a denser region of mesh of the truss at one end going through to the lighter region here. I think this for me really represents a nice blend of going from the simulation and the engineering through to the design process as well. So more than just using the output of a simulation or a generative tool, how the designer can start to influence the outputs from these, and you could use them as information for within the design process. Just to finish off, one of the studies that we did for this project was looking into how we could represent the structural simulation more directly. So, for example, using the streamlines from the compression and the tension within the part, and how we could represent that directly. This was not used in the final Maggis project, but it was motivation and stimulation for us when we came to the LASIMM project and the demonstrator, which Josh is now going to go through the design process for.
So I'm going to talk about the beam design for LASIMM and what we did to get to the ultimate design that we printed. So if anyone's been to our office before, you'll see that it's full of models. It's full of mock-ups and prototypes and interesting material samples that we've been collecting and exploring on different projects over the last 50 years. At the same time that we were getting into LASIMM, one of the big projects in the office was this big Apple store in Union Square in San Francisco, where this big mezzanine that you're looking at is a giant cantilever coming off of that back wall. The slab was acting as a big focal point for the space. It integrates lighting, structure, there's acoustic attenuation, and everything had to be really critically designed with each discipline constrained by both material property and manufacturing constraints. So what we thought was to try and readdress this problem, alleviating some of the issues we had with fabrication, with a 3D printed steel beam that was cantilevering off one of the columns in the office. We thought if this was in the office, it would act as some inspiration to the design studios and also encourage some of the architects to look at integrating different systems into the actual manufacturing processes of the structure. So we started with this idea of a 5-meter beam with some very distinct parameters. And then we started to explore different ways of subdividing the structure, or rather evaluating the structure to give us a desirable design. So we started with basic principles of structural analysis for cantilever, looking at logic-driven distribution of elements to find the optimal forces within a segment, using graphic statics and the Mitchell truss at the top. We also explored analytical models, starting with the input volume and producing a stress field that we could use to generate the appropriate structural elements. And lastly, we tested different topological optimization processes as a means of carving away the 3D volume. So we went through a lot of iterations on this. Some of them were design studies, some of them were structural studies. We looked at a bunch of different prototypes and we made a lot of models, physical 3D prints, and also different ways of manufacturing this beam. We also experimented with Fusion 360 at the time. Unfortunately, we weren't able to integrate topological optimization with buckling, which turned out to be one of the overriding conditions for the performance of the beam. Because obviously, if we're hanging this in the main studio and architects are going to be sitting underneath it and potentially hanging things off it at various points, we need it to be properly designed. So we ended up with a kind of hybrid space where we were using stress field to seed a sequence of curves that we rationalized and controlled for the three-dimensional component of the beam. This way we could use stick models to validate the performance of the beam and ensure it was safe before installing it in the office. So at the same time that we're looking at the overall structure, we were developing details around the node connections, the intersection of the cord with the central mesh, and studying the way the holes would infill when we hit the limits of the tooling part. So when the radius of the tool was too small for one of these openings, it would close. Basically, because we were creating the material and not just removing it, we didn't necessarily have to use circular arcs or square edges. We could curve and round the elements into whatever shape we wanted to minimize the weight of the final beam and really push our design opportunities. This analysis that you're seeing here was done by our in-house structural engineering team, and it determined that the governing dimensions of the beam elements, specifically with regard to the out-of-plane buckling. So they used Galapagos to drive some of the input variables for our parametric system, and then iteratively optimized for the weight of each segment. In the end, we came to a series of tapering elements which we could use as the basis for evolving the rest of the design of the beam. So these dimensions came with a bit of flexibility for rounding corners and edges and manipulating the profiles within a given tolerance. So we were given these shapes and then allowed to kind of refine it as the design required and some of the fabrication constraints required. So on top of the structural analysis, we layered in the different aspects of the manufacturing. So we had some of the additive component, and this was very sort of 2.5D process of adding, so we couldn't necessarily do the overhangs, and we had subtractive restrictions for the diameter of the milling bit and also some clearance constraints from the tooling frame. And so those all played to refine both the depth and width of the flange and also each of the internal member elements. This was all built into a parametric interface because the big idea is that it all has to be adaptable, so we can start with an input set of parameters, weights, fixed points, but also machine requirements, and then we could evolve the design and regenerate new beams based on these new requirements. So if we increase the load or change the depth, the beam would get thicker, the elements would get thicker in places, the tension would reduce the material in other areas, and we would end up with a manufacturable beam that we could change on the fly. This is just a little rendered detail of what we were shooting for. So you can see the tension elements there are quite thin because they have an elliptical profile. That might be a little hard to see in this image. So the square compression elements reduce down to an elliptical section, which then gets milled and refined to a lighter beam. Here's the final 5-meter option that we were hoping to print. So you can see the web in the middle gradually flares to the bottom flange and the top flange, giving a smoother transition of structure from the vertical to the out-of-plane buckling force. And so with each of these iterations, we had to come together as a workshop with the whole consortium to look at the beams and the materials and the interplay of all these different elements and how they were coming together that could be adjusted. One of the other critical workshops we had was at the Autodesk Birmingham headquarters. So they have the actual machines that they could prototype with printing. So we were able to print some little test pieces and also play around with the tool path. So one of the long-term goals was to see if we could integrate some of the ideas that Sam presented with acoustics and attenuation and also thermal properties by introducing porosity into the internal structure of this beam. Also, you can see in the bottom right, there's a giant chocolate Easter bunny, which they did because it was over Easter. But it's just one of the things that goes on there. This is not an edible Easter bunny, it turned out. Still quite cool. So now I'm going to hand over to Johnny, who's going to talk more about the test beams that we started printing and the part that we ultimately manufactured.
Thank you, Sam and Josh, for that overview. I will now explain a bit more about the machine and some of the machine concepts. We as Autodesk were in charge of driving the software, creating the NC programs. We worked closely making the demonstrators with the other partners. The actual hardware was designed and manufactured by LASIMM with the parallel kinematics machine and global robots for the robots, the welding equipment, and the overall integration. LASIMM, the large additive subtractive integrated modular machine, has 3 base components: part rotator in the middle, where the parts are being manufactured. At the bottom, the robots with the additive process, and on the top of the cell, here we have the subtractive capability to do the post-machining after we've manufactured a component. The concept for the additive process was to use a build plate, start building on the plate, and do that on both sides simultaneously. So build on the top side, one layer, then rotate apart, build a layer on the other side, and then rotate back to the previous side. And then keep going until the complete part is manufactured using both robots. The robots, for accessibility, need to have the build plate in a horizontal orientation PKM, due to its orientation and working envelope, needs to have the build plate in a vertical orientation, so the part rotator is a necessary element of the cell. The build plate will be clamped in a picture frame. The picture frames will be made to size for the different demonstrators, and because there are multiple demonstrators, the layout is done in such a way that we can accommodate a collection of picture frames and build plates. The PKM is already existing and has its working envelope at a certain height, which meant we needed to raise the picture frame and the build plate 2 meters height from the ground, and also raise the robot slightly so that we could reach the build plate in the horizontal position. The modular approach for LASIMM is depicted on the right. We chose to have 2 robots working together for increased additive capability and have the machining capability on the right side. Another layout would be to have them side by side and work on 2 components simultaneously. So as the robots deposit on the top end, we could have the machine milling on a secondary part on the bottom side. Finally, the small schematic shows another layout where 8 robots work in tandem on both sides, and we have the PKM mounted to a gantry on top for the post-machining afterwards. Any layout is possible. It really depends on the part you want to manufacture. As said, we used 2 robots. In this case, we chose for 2 Fanuc robots with sufficient reach. Both were mounted on a rail to extend their working envelope. Again, one of the benefits of using robots is they can be easily integrated into a system, and their working envelope can easily be scaled using tracks. Here we used a single track for both robots and used cards where we mounted the welding equipment to. Here we used 2 Fronius welding packs using the CMT process for the WAM DED process. As said, for the subtractive side, we used a parallel kinematics machine. We wanted to have a stiff, high-speed kinematic for the post-machining. This particular machine was equipped with a 5-axis head. Only downside to a PKM is how it's operated. You use different pistons to manipulate the TCP, which means that the working envelope is sort of dome-shaped or umbrella-shaped. And to extend that working envelope, we mounted the whole PKM on 2 auxiliary axes as well, the V and W axis, so that we could have an additional reach and extend the machining working envelope also to 6 by 2 meters. Here we can see a quick time lapse of the integration of the cell. The PKM and its auxiliary axes were already existing, which meant all the other equipment needed to be aligned to that side. And here we can see the fixture going in, and in a bit we can see the laser tracker, which is being used to align everything perfectly to the milling machine on the right side. Here we see the cards coming in, and in a bit the robots are being lifted into the cell. It is really, all the modules are being manufactured in the layout we chose, illustrating the modularity of LASIMM. And if we move to the next couple of slides, we have a few photos of the final layout, how we manufactured everything. We can see the 2 robots on their tracks. We can see the PKM on the right side in the parking position, so it doesn't interfere with the picture frame. And we can also see that the part rotator is quite high up, about 2 meters, which means we need some stairs for the operators to go in case any assistance is needed. We also use cameras to monitor both manufacturing processes. Another picture from the other side, we can see a little bit of the build plate on top. And here we can see the build plate in a little bit more detail after we deposited a single layer using the 2 robots, all looking good. We can also see the camera on the top of the frame, the welding camera, where we monitored the melt pool as we deposited. On the other side, when the part rotated 90 degrees, we have the PKM. The PKM is equipped with a normal spindle, so we can use touch probes, drills, mills, any normal cutting tool to do all the CNC operations. Here we use a touch probe to locate the plate, set the origins, and do any measurements that we need. Here's a close-up shot where we used one of the drills to do some test cuts to see how the parts were aligned on both sides. And here's the final image of the first beam after manufacturing, where Frank and I are inspecting the results we achieved. I'll now hand over to Frank, who will explain us how we drove this system in the software. Over to Frank.
Thank you, Johnny, for this overview. Let's jump now into the software bits for a moment. In this project, we had some major challenges to overcome. We obviously had to drive the different hardware and generate all programs for them. We also had to drive the processes this machine is designed for. In this case, additive with 2 robots, subtractive and probing with the PKM to locate and inspect the part during build. We were also looking at making a simple and repeatable workflow, and of course, produce a few demonstrator components. Speaking about the machine, it's a 22-axis system composed of 2 6-axis industrial robots, each of them on a track. That's the 14 first axes. A PKM machine on 2 tracks that is adding 7 axes to the kinematic, and finally, a part rotator to flip the component. The main challenges around driving the machine was how to deal with parallel manufacturing processes, how to divide the workload, the toolpaths created for the parallel processing between the 2 robots, and how to get these robots working together without collision on a dual-sided component. The secondary challenge was the workflow creation and validation, basically doing the steps you can see here, starting from the desired component, simplifying it for the additive printing, create the toolpath to drive all the processes, including the I/O signals to manage the machine synchronization to avoid collision and making sure all is done in the right order. We also had to look at how to make the component itself. We didn't want it to fall into the trap of adding too much material on the base plate and transforming this into a milling exercise. So the goal was to add enough material to fit the final component you can see in green into the added material, also taking into account the shrinkage of the substrate. The workflow we imagined was relatively simple. First, with robots, the goal was to locate the substrate and align both sides. Then we execute the dual robot additive programs. We then find the part origin, locate where the part is on the substrate and the deformation with the probe. And finally, we execute the milling program using the PKM. The software response to the desired workflow is the creation of alignment routine in robot native language first. For the dual robot additive, we wrote a specific add-in. We also developed procedures to track deformation of the substrate during the additive process. This is the color map you can see on the 3rd bottom picture. And finally, we developed the simulation and the processor for the PKM machine. This brings me to dual robot additive management. We call the technique used zoning. Since we had 2 robots with 2 welders, the goal was to split the work between them, leaving a safe zone between robots for safety. For this, we created 4 zones. Each zone has a different width. Since we wanted to avoid waiting time, the volume of deposition is roughly the same in each zone. So the welding time is the same in each zone, and both robots start and stop together. After all toolpaths have been calculated, this was a step executed, and all toolpaths were marked with a zone, a side, and a layer information. We also get statistics report telling us the amount of time and material per zone and how much welding wire was needed. What you saw previously is basically to share the work between robots. This here illustrates the different settings available to work in safe conditions and avoid collision between the robots and the end effector, but also between the robots themselves. Lots of settings are available, from setting distances and angle to desired head orientation to get a desired and safe result. For repeatability and simplicity, a plugin has been added to the top of the existing Autodesk Power Mill software. It consists of a ribbon, the buttons you can see on the top, a couple of plugin pane on the right, one for additive to drive the robots and one for the subtractive and probing to drive the PKM. There is also on the bottom a replay bar showing the 2 robots in action, including the robot synchronization. So it means robot waiting for each other between changing zone or going to safe parking position on the end of each track when the positioner is rotating. There is a similar user interface for driving the PKM, where probing and milling toolpaths can be programmed, simulated, and post-processed to the machine language. I'm now giving the floor back to Johnny, who will show you the machine in action. Thank you very much.
Thank you, Frank. So here I've put 2 clips side by side. On the left, we can see the software in Power Mill with a screen capture, where we can see the toolpath animation, as Frank just explained. And on the right, we can see some footage captured in a cell where the same 2 robots deposit the program beam for real. So I work in 2 different zones, and we can see the beam slowly being manufactured on both sides. Once one robot is completed, it will go to its home position, wait for the other robot to also finish and be in a home position before we rotate to the flip side and then to depositing on the flip side. Once both robots are done, we will flip to a vertical position where we will then do the machining operations. And again, here 2 videos. On the left, screen capture from Power Mill, illustrating the probing and the machining. operations. And then on the right, we can see the actual machining being executed on the LASIMM in Spain, using a touch probe, first of all, to locate the part, and then a combination of tools to machine the beam, face milling and an end mill to machine the pockets of the beam. Here are a few photos of that result. For this particular demonstration, what we aimed for was to have 1/3 of the beam as deposited, the middle bit rough machined, and the tip of the beam completely finished machined. So here we can see some in-process photos as we machined the tip of the beam and the pockets through. And here we can see the final result, where we've also machined a few slots around the beam so that we could remove the demonstrator component from the build plate once it's completely finished. This concludes our overview of the machine layout and the programming of the LASIMM. We've shown you our proof of concept software built on top of PowerMill. We could use 2 robots to work simultaneously to deposit a large component, and also shown you how to do the post machining with a PKM using both probing and milling. With these tools, we produced several demonstrators for the end users. I'll now hand it over back to Josh, who will close us out with a few final words.
So just to finish off, I'm going to talk about the learnings and what we took away from this whole project. One of the big things that we're going to keep looking at going forward is how do we build more freeform, and how do we minimize the use of the base plate. Obviously in the project, there was a big 5-meter plate that the beam grew out of, but if we were to change the orientation of the piece or be able to actually print from a cantilever, we'd have more flexibility in terms of form, but there's additional constraints in terms of the welding properties about printing horizontally, the weight of the piece as it's growing. And again, with all of them, you have the issue that the temperature in the piece as you're printing is changing continuously. There's a lot of issues to keep looking at. Again, as Sam mentioned, one of the big issues with printing is the added value of these parts. So the big question is, with steel being low value material, the parts need to be high value to justify the process. So in this Apple Store in Union Square, if we were able to produce a beam that operated with some of the other considerations, so integrating the lighting or integrating some of the MEP properties or capacity, we could take some of the costs from those disciplines and integrate them into the potentially greater cost of 3D printing a steel beam. Equally, if this beam was expressed, we'd be taking the place of what is currently cladding and some of the other features. So we're also replacing some traditional processes in this, so cast, forging, rolling. All of these are additional processes that require shipping, that require handling, finishing. And so when we talk about 3D printing a steel beam, this really needs to consider all of those different features in the final composition. And lastly is the milling and energy time. How can we reduce that and only do it as required? So selective milling, there's certain parts when you're talking about a structural column where perhaps only the connections need to be milled. Is net WAM possible? So is it going to be possible to actually print the final piece, second from the right? Maybe you would be able to print holes, but that seems a little extreme at the moment. In any case, I think the major goal is to try and print as close to the end part as possible so that we're doing as little milling, because that definitely took the longest of any process. And with the vibrations and the additional force in the frame, this was one of the more difficult things to control. And so what surface roughness is acceptable, this all comes down to the structure and the aesthetics. And one of the big things to take away is that in order to make a machine like this happening, it required a lot of people from a lot of different disciplines collaborating together, working together, and really functioning as a group. So this picture incorporates all of our different research institutions when we got together with PART. All of this is required in order to make something so comprehensive, incorporate all these different areas of expertise. So to summarize, the way we looked at it, in order to do hybrid manufacturing, you need to have an understanding of material properties. So in this aspect, it was 3D printing and what happens as you're depositing material and how the material transforms in its liquid state to its solid state and everything in between. There's the machine design. So having additive and milling in the same feature. Does that part move? How do we make it adaptable or compartmentalizable so we can replace certain features and use it for as many different applications as possible? Structural optimization is a critical part of doing hybrid design because we're not talking about sticks and 2D analysis anymore. We're really getting into three-dimensional freeform, and there's a lot to understand as designers, but also as engineers and manufacturers about how this informs parts. The fixture design is really critical, so obviously that impacts on the forms that we're able to produce and also the types of manufacturing that we can achieve. And the hybrid manufacturing software is essential. So what Autodesk was doing was pulling together all of the different pieces of expertise and linking them through the actual operation of the robot. So the toolpath and everything that comes out of the software will affect the design, it affects the structural optimization, it's informed by the fixture, and obviously has a really big impact on the material properties. So every one of these elements really has to work cohesively in order to do hybrid design. And finally, from a designer point of view, the actual texture of the toolpath is something that I think we're only just barely starting to get a handle on. I think there's a lot of opportunity for us to explore different toolpaths and weaving and stacking. There's loads of things that we can start to explore to see how we can reveal that on projects to reduce the amount of additional cladding and minimize the overall embodied carbon of our projects by looking at the raw materials. So we did this little video that'll play now, which shows how we thought this manufacturing process could be used to inform different parts of a project, starting from a stair where each step is slightly different, to mezzanine, extending this cantilever idea to the roof, supporting different types of structure, and ultimately leading to more structural forms because we don't necessarily have to rely on the typical extruded profiles that are currently so ubiquitous. So I'm going to end there and say thanks from Sam and I for listening, and I believe now we go into Q&A.